All right, ladies and gentlemen, let's get ready to rock and roll. We have recently covered all of the information that surrounds graphing, and then we added how to graph using derivatives on top of it. Okay, so let's do a quick review just to make sure we get the itemized information that we should already know, and then we'll go through and we'll do a quick example at the end. Hopefully it won't take us too much time. All right, guys, let's jump right in. So if you look at it, the information we need is basically all of the information for the first derivative and the second derivative. So just reading through this really quickly, each one of these have their own specifics. And what I mean by their own specifics is that the critical values are just the zeros for the first derivative. Right, so if we think about like a sign chart, the zeros are the x-intercepts, so they're the zeros for the first derivative, and the non-differentiable points are the bad numbers or the undefined numbers. Okay, so but for which function? That's for the first derivative. Yet again, emphasizing the first derivative, okay? And then finally, we need to know the integrals of increase and decrease. Well, what does that mean? Well, that means make the sign chart of the first derivative. Well, all that information, but to make a sign chart, you need that and you need that. So I'm just going to say, in order to do it, just simplify all this. One, make the sign chart of f prime is the first step when we're adding the calculus to the 1800 definite way of graphing. And I'll actually go through that when we do the example. And then we're going to do the inflection points, which basically means you need to take a look at the sign chart of the second derivative. Okay, really simple. If you could do those two things, and we will be making those two things, in addition to the other 1800 stuff, then will be the pre-calculus is what I was trying to get you. Pre-calculus graphing methodology, you'll be fine. So let's cover it as a whole. So the information we need from calculus is sign charts of f and f double prime and f single prime, and that's going to be in order to graph the regular function. So to graph f, that's the function we're graphing, we need to find the intercepts of f. Just the intercepts. That's something that's typical of pre-calculus, was find the intercepts. Asymptotes for sure was a pre-calculus thing, but this is where calculus takes over, because you better know how to find the asymptote by taking the limit as x approaches a number of that function, and if it hits infinity, then you know you got a vertical asymptote there. And you got to be careful, because now we have functions where you get 0 over 0 over infinities, and they're not the same vertical asymptote kind of shindigs that we've seen in 1800. Why? Because in pre-calculus, all the functions were easy, because you couldn't have really difficult ones. Now we do have difficult ones. Your horizontal asymptotes, the calculus way of doing this is taking x as it goes to plus or minus infinity, and then seeing if it equals a number. If it equals a number, great, then we have a horizontal asymptote. If it doesn't, then it just blows up or blows down, depending on whether or not it goes to infinity or negative infinity. Okay, and these are the two guys, f prime and f double prime. So really, it's just 4 pieces of information. Those 4, and then I always like to find the critical values, those that have high points and the low points in the graph, by looking at the sign charts, right? And we'll do this so you guys understand where I'm getting all this from. So those are labeled, and then finally graphing. Okay, and if anything, you could even slide on this one sometimes, depending on how good your drawing skills are. A lot of people don't have drawing skills. So let me go through, and I'm just going to re-highlight all the basic info you're just going to need. Intercepts, that was done by sending the actual function equal to 0 and solving. But everything else requires calculus. The asymptotes, that's a limit problem, and that's another limit problem. Okay, then the sign chart of the two f and f double prime, f prime and f double prime, to get the critical values and inflection points, and then find the critical values, and then finally we'll graph. Okay, very simple. All right, so let's do an example, and let's hope we don't get a brain aneurysm. And it normally, when I say brain aneurysm, it's not meant to scare you, but it is meant to say that these are long problems. And if you ever say, well, man, am I ever going to have time for that? Yes, you will. Make sure to write it in. All right. So let me recall to you the things you need. The first thing is just your normal intercepts of f. And after all, what's the job here? We want to graph f, but do it in a very cool way now, not just using what we did in in the class previous. All right, you need to find the intercepts. There are two types of intercepts, x-intercepts and y-intercepts. Y-intercepts, you set the x equal to 0. This is Math 1800, ladies and gentlemen, and that gives you that as 0. And then for the x-intercepts, you just got to solve. So that's when y is 0. What is x? So if I make y equal to 0, you get x cubed minus x squared. I'm getting 0 and 1. So that's what I'm getting, 0, and I'm getting 1. If you don't believe me, try and do the work yourself. I just only have one screen to really put all this on. So, all right, so intercepts, second thing. Asymptotes. All right, how do we find asymptotes? Well, pretty simple. It's found by taking the limit as, so I'm going to do horizontal asymptotes first. And most of you should already know this guy does not have a horizontal asymptote because there aren't any denominators. Asymptotes only occur when there are denominators and there's some fights going on. So the limit as x cubed minus x squared, that thing goes to infinity. Well, you notice you're going to hit an indeterminate form. And then the method of dealing with that is force factoring out the highest degree. 1 over x. And then when you take the limit of that again, I'm going to erase all of this, by the way, because the space is important. So when I take the limit as this thing goes to infinity, that gives you a big old number times 1 minus 0, and that is just infinity. Done. So bottom line is that when we try to find the horizontal asymptote, we end up getting, so this is your HA, it gives us infinity, and that means there are no horizontal asymptotes at infinity. If you go to negative infinity, you'll see it's the same thing too, and you should. Vertical asymptotes. Well, first thing you have to do is find them. Well, the vertical asymptotes for this problem, we found where the locations were by setting the denominators equal to 0 and then solving, but this is just 1 in the denominator, so there's none of these. Okay, so easy. So the second piece of it is easy. Okay, now here comes the fun part, and that is first finding the first derivative and then the second derivatives, because you're going to need both of those. And then finally, after we do that, we're going to now need to figure out what the actual graph is going to look like. So this is going to be fun. So this is the deal. So this is what I'm going to do. I'm going to collect my information up here. So x-intercepts are 0, 0, 0, 1, 0, and then 0, 0 is the same thing. So these are just intercepts. And I'm going to clean my board. The horizontal asymptotes, we said there are none. And then we also said there are no vertical asymptotes. And this is how we came to those conclusions. All right, so now let's clean all this up. And then we can start all over again. All right, so what are the two things now? So we're on steps 4 and steps 5. Steps 4 and 5 require those derivatives. So here we go. Normally when this quiz comes around for my class, I always tend to only give them one problem because it's just that involved. It really, really is. Here we go. The first derivative using power rule is 3x squared minus 2x. And again, I need to figure out what the zeros and what the undefines are. And remember, the zeros, what are the zeros? Okay, the zeros are your critical numbers. And that's where the horizontal tangents are occurring. The reason why they're called, by the way, why they're called critical numbers is because normally in the real world, when things max out or bottom out, those are critical values that mean that something's getting ready to change. It's about to change growth rates. That's when it all started with the economics, right? You buy and sell, right? Buy low, sell high. But how do you know when it's gotten to the lowest spot? That's kind of what we're saying. All right, so critical, which is the zeros, right? And that's setting the derivative equal to 0. And then I'm going to solve this, so I get 3x squared minus 2x equals 0. So effectively, that is x equals 0 and x equals 2/3. So those are the zeros for this guy. And if I try to find any undefines, and undefines here, the undefines for the sign chart, because we always do need them, those are your non-differentiable points, which are either a sharp point or a cusp, right? We talked about that. But there are none here because if you set the denominator equal to 0, there's none of those. Okay, so what we found are the two critical values. What I really do need to get, though, is the sign chart. Okay, so here we go. Here's the first guy. So here's f prime. f prime, and literally this information needs to be on there. So I'm really going to put it on there, and then we're going to get rid of the sign chart. I'm going to put in 0. I'm going to put in 2/3. And I know this is and I always got to label stuff. This is a 0, and that's a 0. And the reason why it's called a sign chart is because we don't know when it's positive or negative. So I plug in stuff back into my original function, original function of the first derivative, that is. I plug in something really negative, I end up getting something positive, and then I get a negative, and then I get a positive. Okay? I know fancy math, and that's why I could do that pretty quickly. All right. So once I have this, we're ready to rock and roll. And those are both zeros. Okay. These are, and remember, we're talking about the first derivative. So the zeros are horizontal tangents. Horizontal tangents, right? The undefined are places where they're going to be sharp points. Why? Because the first derivative sign chart talks about slopes. Slopes. Big deal. All right. Moving on. So that's that piece. We haven't even gotten to the point to graph f yet. So yes, is it more detailed than 1800? Absolutely, absolutely. The funny thing is I erased information that I needed. Isn't that nice? So now, that was step 3. And now, let's do step 4. What's step 4? Well, we need the second derivative now. And yes, we should have kept the first derivative. The first derivative was 3x squared minus 2x. Well, take the derivative again. That gives you 6x minus 2. Okay, so this is relatively easy, and you can tell there's going to be no undefineds here, but I'm going to go through the rigmarole of writing things out. If the zeros for the second derivative are the inflection points, so these are your inflection points. That's when you set, so that's where it's going to twist and turn in space. Okay, so that's when you set points. That's when you set f double prime of x equal to 0, and you solve. So we get x equals 1/3. And then your undefined numbers, and what do the undefined tell us again? They're not just, I wrote that on the wrong level. Undefined numbers, what do they give us? Well, they don't give us inflection points. Well, when a second derivative, which is concavity, is undefined, it could look like a number of things. But most of the time, it's just something that you're going to have to read into to actually see what's going on there. So those undefined critical values are huge. All right, when they're not customary, normally they occur at non-differentiable points. So this kind of will be backed up by the first derivative's non-differentiable points. So it'll be the non-diff points basically if they do occur. But the way you find them is the exact same way. You just set the function's denominator equal to 0, and you'll see that when you set it, it does not become undefined, right? It's just 1. So this is none. So they have none of these. All right. Anywho, so that's what I need for the second derivative. Here's the second. Oops. Here's the second derivative. Let me get this. So now we got 1/3 here. Okay. And this is a 0 as well. Okay. Now, what is the sign chart for this guy? Okay, and I don't do any of this information on the left. Absolutely not, because I'm not trying to graph f double prime or f prime. I want to graph f. I just needed all that information to graph f. Okay, and I'm going to switch to red. I know the video is running a tad long, but on this one problem, but this is what the time it takes. All right, so now we are in a place, and we need to do the sign chart here. The sign chart here is, let's see here. It was 6x minus 1 was the original second derivative. So left of minus 2. Left of 1/3, so let's say 0 will be negative, and this will be positive. So now, this is what we did all of this work for. Okay, by having this, now we can finally make a more detailed, and this is what this really is. In 1800, we said all you need is intercepts, asymptotes, and sign chart. But the reality is we don't know what the sign chart really looks like without knowing what the first and second derivative is. So this really is just finding what the function sign chart is going to look like. And this is what we need to start graphing. So this is what we want. We want the true sign chart. Okay, but what do I mean by the true sign chart? All right, well, every critical number you see for the first derivative and second derivative, so the inflection points and critical numbers, they are all important for the actual function itself. You have to go in, you have to use them in order to graph, right? When are they turning, going upward versus downward? We're going to go through all of this. All right, so I want you to plot all of those guys on here, but keep track of what is what. Okay, 2/3. And maybe this is, and I'll try to detail out what the graph will look like. All right. So let's just look at the first derivative, okay? The first derivative, to say that it's positive, means what in terms of the graph? Well, if you have a positive first derivative, that means your slopes are positive, right? Which means it's increasing. It's going up in the sky. So that means, watch what I write here. This is increasing here, and I'll just put increasing. Increasing. And then on this side as well, it's increasing. Okay, and then what's happening for the first derivative in between 0 and 2/3? So it's negative, so that means it's decreasing between 0 and 2/3. So notice it covered multiple intervals. Now, why the interval break up? Because of the second derivative. So now, let's look at the second derivative. The second derivative says that it's negative here. Remember, what does the second derivative give us? Concavity. So that means if it's negative, it's going to be concave down from 0 to 1/3. So from negative infinity to 1/3, and then from 1 to 1/3 to wherever, it is going to be concave up. Okay, and I know you guys are probably saying, wow, that is a lot of detail. We're not even done with the detail either. We're drawing the most accurate graph we can draw. We now need to label these critical numbers. Are they maximums? Are they minimums? So now what does a plus and minus mean? A plus and minus means that the slope was increasing. It stopped. It's 0. Whoop. The slope was increasing. It stopped at 0. And then it started decreasing. So it's plus minus 0. So it is going to be a maximum. That's what it'll look like. So it'll look like one of these little hills. Look at the next one, which is 2/3. Is that a maximum or a minimum? Let's see. It goes from decreasing to 0 and then all the way up to increasing. So that's going to be a minimum. Okay? Now, easy. Now, let's talk about the second derivative. The second derivative, which is this guy. What's his zeros? Oop, that's too dark. I can't even see that. What's his zeros? Well, his zeros, the second derivative, guys, tells us what? Where it goes from twisting like this to like this, except it's on a like an angle, right? It's not like a horizontal tangent. It's twisting in space, so it's going from opening downward, concave down to concave up, and that would be the point. So it's going concave down to concave up. So it lets you know what it should look like at that point. Okay, very, very cool stuff. Very, very cool stuff. We don't know exactly. These little changes in space, this number is not important. All you need to know is that that's what it needs to look like. There's not really a name for this. There's not really a name for it. Okay, now that we have all of this detail, let's finally graph the function. Yes, it is 20 minutes in. I know. All of the detail is necessary. So the thing in red, it was given all the detail by all the 1 by 3 and 4. To make the true sign chart of the graph. All right, now here is the go time. Let's finally graph it. 0 would be here because 0 is there. Here's the x-axis. All right, start with number 1 and put it on there. 0, 0 is an actual 0 of the graph f, right? It's x-intercept, and so is 1, 0. But remember, we had to line these up perfectly. So 1 would be out here. Okay? We said there's no vertical asymptotes, no horizontal asymptotes. Thank goodness, right? Now, here's the real sign chart. Everybody check this out. It is increasing, which means it's going upward, but it's going upward, bowing down, concave downwardly until it gets to 0. So it looks like this. Increasing, but bowing downward. See how it's bowing downward? But from negative infinity to 0, so it should keep this shape. Now between 0 and 1/3, we're gonna have to make some hash marks here, and 2/3. 0 and 1/3, it is decreasing concave up, so it's decreasing going that direction, but it's decreasing also concave down. Sorry, I didn't read that correctly. Until 1/3. until it hits this point in space. Now, what point is that? Well, that point is at 1/3. Now, 1/3 is where the concavity changes, and it's now decreasing concave up. Yep, up. That's a U. So it's decreasing concave up until 2/3, and where it's 0. See that? So this is 0 here because of this guy. This guy is 0, but it's a horizontal tangent there at 2/3 as well there. And now, as it goes to 1, because it has to go back up, well, it's going to be increasing concave up. But it never goes back concave down. So you got to let it go up forever. So not only do we now have points that are off the axes, we have the points of everything else as well. So on the next videos, because we spent so much time articulating where this one came from, which really came from those two came from the first and second derivatives. On the next video, we are going to spend a tremendous amount of time on one example. We'll probably spend 20 minutes on this one example, and we'll flesh out all the little details, and it'll be as clean as possible, all right? So with all that being said, we don't forget, you also got to find your those critical values where the bottoming out points are. Which here it was 0, 0. We knew that, right? But this guy was 1/3. And plug that into the original function, get the output. Same thing with this guy. But we'll talk about it in the next video. There's a lot to do in these problems if you haven't figured it out. All right, guys. I'll see you on the next video. Click it. Let's keep it going. Bye.